Great pleasure to be back in Cambridge, and I thank the organizers. So, I would like to start with some motivation. So, we're going to work with M compact complex manifold. And so, remember there is a, if you have the complex structure, then you're going to get J inside the endomorphism bundle of the tangent bundle of M, which is called the almost complex structure. Remember, this is just acting by multiplication with the square root of -1 using identification between TP and CN. This complex dimension N. This is well defined because you have a complex structure. And it's we will use this way of thinking about the complex structure in the lectures. And also remember that integrability means precisely that such a J, which you could have more generally, square into minus the identity, actually comes from a complex structure, a genuine complex structure. And the condition is that if you use the type decomposition induced by this endomorphism J into the eigenvalues of J, and you have minus I eigenvalues, which we're going to call 0, 1. The integrability condition is that these are closed under the Lie brackets on vector fields. So if you have this differential condition, then actually such a J comes from a genuine complex structure. We'll use this way of thinking about things. Okay, so then you have this basic problem of constructing a space in some appropriate category, which you can call a moduli space. It's something which only depends on the underlying C infinity structure, so on the manifold structure on M. So I denote like this, which parameterizes integrable almost complex structures, or complex structures on M. So you have some minimal requirements. So firstly, you want the points of this space M, whatever it is, should correspond one-to-one to isomorphism classes of complex structures on M. So they are in bijection to complex structures, integrable J's on M up to isomorphism, which means a biholomorphism. And secondly, another minimal requirement is that if you have a family of such complex structures, so it means actually a holomorphic family of complex manifolds with underlying C infinity manifold M C infinity. This is inducing a map to M. So there are some minimal things you might ask. The problem is that immediately, so after a little thinking, you realize that even if you can construct such a M, in general, it will never be separated. It will never be Hausdorff. So such M, in general, cannot be Hausdorff. And the reason is you get this, generally this phenomenon which is called jumping of the complex structure. Which means just this, you have a disk. You have some fixed point inside your disk. You have a family. So the general member is just isomorphic to M. So the complex structure stays the same away from the origin. But then when you specialize to this special point in the disk inside C, you get some M naught, this special fiber, which is still a complex manifold, so no singularities, but it's a different complex structure, so it's not biholomorphic to the general fiber. So maybe it's good to have an example of this. So this is a construction which will come up again later on. So let's take as the underlying C infinity manifold is just a disconnect sum. So we have some basic copy of a complex projective plane, and then maybe M copies of CP2 with the opposite orientation. And this is, if you know about these things, it's the underlying smooth manifold of an M-fold blow-up of P2 at a bunch of points. So for if you blow up more than 3 times, then as a continuous family of distinct complex structures, and for each one of these M will be isomorphic to, so this is the blow up in a collection of points of P2. If you move around the points, if there are enough points, more than 3, then generally 2 of these choices will not be isomorphic. And then if you choose, you can choose this collection appropriately together with.
Wait, doesn't it have to be M larger than 4?
Say again?
Doesn't it have to be M larger than 4?
Right.
So these are the Peso surfaces in general.
Not counting the first, right?
No, yeah, this is M is how many times I'm blowing up. Yeah. And
so you start getting moduli for the Pesos of TV5. Or maybe it's isomorphism and complex structures.
I can use
Okay, you can send any 4 points to any 4 points.
Yeah. That's true.
So it's the same, isomorphism.
Yeah.
Of complex structures.
Yeah, it's okay. It's anyway. If you're going to choose many points, so it's the minimum number.
No, the reason I ask is because to me it's not clear if complex structure is the same as having isomorphism algebraically. I just don't know. I suppose it is not.
Yes, I think. I think it's the same. Yes, it's the same. You're right. Yeah. but we want to blow up a large number of points in general, so the minimum number is, you're right, it's okay. Yes. Yes.
Could you repeat what is about?
Opposite orientation. You know, a complex manifold comes with natural orientation, because the determinants of transition functions are positive, right? So, and you can choose the opposite of that orientation. So if you want to see this, this is an exercise in Albrecht's. So Daniel's book on complex geometry has this exercise that you can realize that it's a diffeomorphism type of a blow-up, and it's given by this. It does everything very explicitly with charts. And
So this is blowing up.
yeah. It's differentially it's this, and this is the complex structure. It's one of the complex structures you get. And if you move around the points, this connect sum stays the same up to diffeomorphism. The complex structure in general will vary if you have enough points. Let's say more than 4. So then we are safe. Okay. So if I choose this collection of points, well, I choose more than 4. I choose maybe 100, and I choose lambda, one PS, and one parameter subgroup, just as in the previous lecture. So this is a map from, say, C star inside the PGL 3C. So the automorphism group of CP2 suitable 1PS. Then I can move these points using lambda, and then in the limit, you know, in the limit these points will become a line, so they might end up just on a line inside CP2. Whereas so this will be the limits, P1 bar, P2 bar, Pn bar. And here you have this connect sum operation, which is just the blow up inside each copy of CP2 bar. I have the exceptional divisor depicted here. So you start with a collection of points which is not aligned, not all lying on the same line. But if you choose them appropriately together with lambda, this one PS, you can squeeze them down on the same line. And so in this case, the complex structure will jump. One way to see this is simply that the group of automorphisms as a complex manifold will be larger when you specialize to this configuration here. It jumps. So this is M naught in our previous notation. And so M will not be isomorphic to M naught in general if you choose the collection and the lambda so that this can happen. So this is a basic phenomenon that you can see happening to complex structures. Okay, so we need a way to fix this. And, there are various ways to do it. I'm going to talk a bit about the differential geometric way to do it. So I'm going to discuss polarizations. The basic idea is that you want to make things more rigid, so this such degeneration should not be allowed, should not be admissible families when you construct your space. These families should not be allowed because you rigidify things sufficiently. And one way to do it is using this idea of polarizations. So now remember we are starting from Mj, which is a complex. Should I turn this off? Okay, it seems fine now. Okay, so I'm going to also have a Riemannian metric then. So a Riemannian metric G is, well, initially it's a mission if J is a G isometry. In other words, if you try to do J combined with G, this stays equal to G. And this is just some algebraic condition. You can always find the mission matrix for some given Mj. So this is just some algebraic condition which you can enforce. Well, much more rigid than that is the basic differential geometric compatibility condition which you can impose, and it's precisely that. One way to see it is that the almost complex structure tensor should be parallel, so this should be 0. So this is the Levi-Civita connection of G acting on J. So now once you have a Riemannian metric, you have Levi-Civita, which is initially it's acting on vector fields, but you can promote it to act on any kind of tensors, just by the Leibniz rule. And so you make it act on J, which is a tensor after all. It's some section of a tensor bundle. And the condition is that that should be as compatible as possible with the metric, so that you get it's a parallel. J, the lingo is that J is parallel for the Levi-Civita. Then, if you have such things exist in abundance, we know that it's a very well known fact that if you have any projective manifold will have such a structure, and in this case you say that G is scalar. This is a scalar structure, and such structures exist on all projective manifolds, for example, but even more generally. And then you have, out of this construction, you get the metric 2 form. Omega, which is simply given by composing the metric with the almost complex structure tensor, and you place it in the first index. This is omega acting on anything. So this is alternating. So omega is Q because G is Hermitian. So just using that, simple exercise if you want to check it. But also more fundamentally, it's closed because of this parallelism condition. So you can use that to show that omega is closed. So it's a closed 2 form. In particular, it's also symplectic because it's non-degenerate. And this is because G is Riemannian, so it's non-degenerate. Okay, so it defines a Taylor class. So you get out of this structure, you get some cohomological information, omega, in H2, there are M. So it's actually with real coefficients because everything we did was a real construction so far. And if you're interested in that, you can actually show that this also lies in H11 M in terms of Dolbeau cohomology. But let's see if it's a few. Know a little more about complex structures. And now, so we call triple of such M, J, in such a class omega, so some class in H2 which is realizable as the metric form class of some Kähler metric, we call it polarized. A polarized complex manifold. Now, I think some people would insist that actually omega is, they would reserve polarized to mean that omega is also a Hodge class, so it's not, here I get Q and not R, but for us it would be just real in general. Okay. So in this case, this is the category of manifolds that we want to work with. So we rigidify things in this way by fixing these polarizations, these Kähler classes. And I claim that it's a useful thing to do. But in order to explain this, I need to tell you a little bit more about curvature. So, for example, we have a Riemannian metric. Basic quantities are Ricci and the scalar curvature of a Riemannian metric, and they both become much more manageable in this Kähler situation. So, for example, if you're interested in the Ricci G, and you remember Ricci of G is some quadratic form. Which is defined purely using the Riemann curvature tensor. It's kind of trace of the Riemann curvature tensor of G. You get a quadratic form out of it, which is pretty fundamental. You call it Ricci. And this is determined by something which is this is symmetric quadratic. It's determined by something which is alternating, which is actually skew. It's a two form, which unsurprisingly you call the Ricci form, which you denote Ricci omega, and which you can show is given by this thing. With respect to any set of local holomorphic coordinates. In local holomorphic coordinates. Okay, so that's the formula. If you remember something from Riemannian geometry, the expression for the Ricci curvature in coordinates is much, much more complicated than this. So this is a very special feature of Kähler geometry. You see that Ricci curvature becomes expressible as some kind of complex Hessian of some quantity, and this quantity is log det of the metric. And this is one piece of curvature, and then if we take the trace of that, we get the scalar curvature.
Excuse me, could you
Yes.
move the board up a little bit? Sorry.
Which one?
The rightmost.
This one.
Oh, that one.
This one should go up. Okay. This way.
And that one should go up
Okay,
a little bit
sure.
more. Just because of the.
Sorry, because of the lectern.
Thank you.
I wonder if anyone ever uses this connector, like German philosopher or something.
Could you just read what is in the last bracket? The log that what?
Yeah, so this is the metric. So you the Riemannian metric, somehow you can write it with respect to these complex coordinates. It becomes some Hermitian matrix, n by n Hermitian matrix, with some entries which I call G, K, L bar. Yeah, you take the determinant. So this is in local coordinates. So if you take the determinant of that, it will give you some function which is strictly positive, because G is a Riemannian metric. So I can take log of that function, and it's well defined because of that. And then I take this kind of complex Hessian of this function. So it gives me some. Yeah, okay, sorry. I guess I should probably. What you mean is probably I forgot the form part, right? This will be just this entry. So either I do that or I put some form part here, as you prefer. So maybe easy batch. It's a two form then, but it determines completely the symmetric quadratic form, which is Ricci. If you just contract with the almost complex structure tensor.
Can I also ask a question?
Yes.
So I would call so what I've seen before is like a polarization on a symplectic manifold is a choice of like a Lagrangian.
Yeah, it's unrelated to that.
Sorry?
It's a different thing.
It's a different thing.
It's a
Okay,
different
so it's
thing,
not
yes.
like somehow this data is not.
No, it's not like an integrable system, so it's different. Unfortunately, there are only so many words.
Yeah.
Yeah. And yeah, so there's also this scalar curvature. Then it's going to be also computable in terms of this alternating two form, and so it's just a trace of that. So did I leave out a minus sign? Yes, I think I did. Sorry about that. I left out the minus sign. It's very important. So it's this stuff. So once again, if you remember, local expressions for the scalar curvature tend to be very complicated in higher dimension. And in the Kähler case, they simplify a lot. They become like this. This is just the inverse of the matrix, which locally is telling you what is the metric G. Representing G. And this is more similar to what happens in dimension 1. In dimension 1, if you think about the Gauss curvature, you get expressions which look a bit like these in the Fermi coordinates. And they are precisely the same, because in dimension 1 everything is scalar. So you can check that as an exercise, if you like. And you would recover those expressions in terms of isothermal or Fermi coordinates. But in higher dimension, usually you don't have those. You have if G is scalar. Okay, then what happens is that you get these fantastic formulae for basic metric quantities, but also you get some cohomological information, because from the local expression, it's pretty easy to see that this Ricci alternating form is actually automatically closed from the way it's expressed as this compensation. So you can check that if you take the round differential, then it's 0, and moreover, the cohomology class it represents is inside H2, the RAM. And once again, you can check, if you know a little bit more, that it's in H11, with respect to those both, is independent of the choice of omega, as long as it lies in the same Kähler class. So if the RAM cohomology class represented by omega stays fixed, then also the same is true for Ricci. And in fact, it's true that this is okay up to some constant, which I will probably mess up if I try to. It's some 1 over 2 pi, but let's leave out that. This is just the same as the first chain class of M. So it's you should take 1 over 2 pi Ricci, you get the first chain class of M. If you can define it this way, you can define it topologically. They are the same. So why is this useful in view of our motivational story? Because you can then use these metric quantities to define some nice parameter spaces which are automatically separated, Hausdorff. So it gives you a differential geometric answer to this basic non-separatedness problem. Let's see some of these theorems. Some of them are very classical. So there's a theorem which is due to Georg Schumacher, I think in the 80s, that there exists a Hausdorff complex space M, which is a modular space in the sense that it satisfies these minimal requirements 1 and 2. So let me just write parameterizing in the sense of properties 1 and 2, polarized manifolds and J omega, provided one very special thing happens, so such that the class represented by omega is minus the class represented by Ricci of omega, and that's minus the first chain class of M. So if you like, this is the canonically polarized case. So this is the case when omega is the first chain class of a metric on the canonical class, the canonical bundle. So if you know a little bit about positivity, it's the case when the canonical bundle is ample, so a curvature defines a curvature of any initial metric you put on it defines a Kähler form. Well, you can find some metric on the fibers of the canonical whose curvature defines a Kähler form. But we don't actually need to know that. You can just decide that your definition of the first chain class is the class represented by Ricci for any metric. And this is the favorable case, so the sign turns out good, so that you can get separatedness from this theorem. And similar to that, there's a second theorem also by Schumacher from perhaps a little later on, which is the same for families of polarized manifolds. Well, now we don't have any restriction on the Kähler class omega, but we have a strong restriction of M. It should be Calabi-Yau in a weak sense. That so as long as the Ricci, the class represented by Ricci is 0, which is certainly possible. Ricci just said it's close, but it could very well be exact. And this is the Calabi-Yau case. And let me just say that the reason why these theorems work is that they rely on Yau's proof of the Calabi conjecture. So they are differential geometric, so these theorems use the Calabi-Yau theorem. So they use crucially the fact that you can find metrics with special curvature properties, in particular so that the Ricci curvature is constant. So you would expect that they could be subsumed into some bigger theorem that replaces Calabi-Yau with some other curvature condition, and that's been done. So let's see where. Maybe I should go.
So this M is Not compact. The house of complex space.
No, it's no. It's very. I mean, it's not very non-compact. Yes, we only parameterize
It's very
smoothly.
non-compact.
Yes. We only. This is parameterizing manifolds, not so they are all smooth, and so you would expect that. So it's much. It's kind of foundational. You wonder if you can at least construct something which is separated with these minimal properties. And you can have a more general theorem which uses a different curvature condition but applies potentially much more generally. If you replace the Ricci curvature with a scalar curvature. Let's see, the theorem. Okay. Which is due to Fujiki, Schumacher, and then with some extra assumptions, and then this generality to Dervan and Neumann, which is the following. So the same is true. So same means that there exists such a Hausdorff complex space with basic properties 1 and 2 for polarized manifolds. So triples like M, J, plus omega, but such that a certain curvature condition holds that the scalar curvature of the equation that the scalar curvature of some representative of this class, some metric representing this class, can be chosen to be constant. Is solvable for some omega representing its class. So if you're happy to enforce some curvature condition which looks pretty natural, in complex dimension 1 it would be choosing a hyperbolic metric, like choosing the Gauss curvature to be constant. In higher dimension you can enforce such a condition, and then you will get a nice, at least you can some fundamental modular space in that way. Okay, so maybe I can start telling you a little bit why this is true and how it relates to stability and so on. And the basic reason why such theorems work is a moment map picture for the scalar curvature, which is due to Donaldson and Fujiki. So let me go into that a little bit. Let me call this the Donaldson-Fujiki moment map. It's really the main conceptual reason why you get this K-stability notion from a differential geometric point of view. It's very hard to motivate if you don't have this picture in mind. So once again, we have our this compact complex, and now we fix some representative of a Kähler class, so it's a Kähler form. in particular, it's a symplectic form, and you have so we have a space. Let me just call it J. It should be more precisely J omega naught, keeping track of this reference point, which is given by omega not compatible J. And that just means that if you J preserves omega naught, so if you plug in J, this symplectic form stays the same, and also that if you plug in J just in one of the two indices, you get something which is then positive definite. It's Riemannian. So we're not asking J to be integrable. It's just a space of all smooth C-infinity almost complex structures, so endomorphism squaring to minus the identity of the tangent bundle, satisfying these sort of algebraic conditions. So there's okay. So this is there are some foundational results. So this curly J is some infinite dimensional Frey-Hilbert manifold. And it's pretty clear that it should be infinite dimensional because such J are C-infinity objects. Locally they're just given by a bunch of smooth functions, so you can choose them in a smooth way, which gives you infinite dimensionality. Well, we're not going to go into the technical details of how to handle this infinite dimensional manifold. It can be done. And then if you believe that, then J comes with something called the almost complex structure, almost scalar structure. Which simply means that there is an almost complex structure which is tautological. So let me denote it by bold J. So this bold J, well, it should be some endomorphism of the tangent bundle, so it should go to this tangent, this fiber of the tangent space to itself, and you have some tangent vector here, which we will call A in what follows. It's just sent to composition of pre-composition, post-composition J with A. So this is how it acts at the point J. So at point J is a multiplication by matrix J. And of course this varies when you move around this space, and at different points we multiply by different matrix, so this J is certainly non-linear in this way. And also a symplectic form. Let me call it big omega. So I should tell you how it acts at a point J in this big space. And that's just the integral of your manifold of the trace of J, A, B. With respect to the volume form, which is defined once we have a symplectic form. Right? If you have a symplectic form, you raise it to the top power, maybe normalize, and you get a volume form. That's one you can choose the normalization you like, but this one is convenient in Kähler geometry. And these two things, they satisfy formally the properties of a Kähler manifold, that you can make sense of the Ramp differential acting on such omega, and it's zero. It turns out to be closed in this formal sense, although we don't really need it now, but it's true. So this is what makes it not just symplectic, well, it makes it symplectic and then almost scalar, because this big complex structure J is also formally integrable in the sense that it defines some distribution which is formally integrable. In the sense we discussed at the beginning that such a distribution is involutive. So what you don't have is the property that this, so you don't know how to go from that to actual integrability because you're in infinite dimension, so there is no theorem telling you that if that distribution is involutive, then you can find a local holomorphic chart, but you don't need that for this Donaldson-Fujiki picture. So you get this big space parameterizing all almost complex structure compatible with some underlying Kähler form, and it's well behaved in the sense it inherits a sort of Kähler structure from certainly a complex structure and also a Kähler form. But it's infinite dimensional, so you don't have any standard theory about these things. Okay, so now we speak of moment maps. It means this should come with a group action, and it does. So there is a group of exact symplectomorphisms let me call it curly G. It's also usually denoted by ham omega naught, and it's defined as time 1 time t equals 1 flows of time dependent Hamiltonian vector fields. Of omega naught. So it means that you have a time-dependent family of vector fields. Let me call it xt or x phi t with respect to omega naught. This is the symplectic gradient of this function phi t with respect to omega naught. And f is t equals 1 flow of this time-dependent family. So remember, if you have a function on a symplectic manifold, you have this notion of a symplectic gradient, right? You can represent the differential of phi uniquely with a vector field under the duality given by the symplectic form. It's just contraction in the symplectic situation. So you get this notion, and this gives you a notion of symplectomorphisms, which are more than just symplectomorphisms. They are actually induced by Hamiltonians, by functions with this construction. And but in particular, they are symplectomorphisms, so they preserve omega naught. And so G, in particular, acts on this big space of complex, almost complex structures J, just by pullback. So you have J, how do you want to call the action? Dot, J dot, sorry. Let me call this some element in here, G maybe. So G dotted with a almost complex structure J is just the pullback of J, which is just the composition of with the differential. Okay. So, what is the theorem in this situation? Okay, so maybe. Okay, let me write it here and then we can have some sketch. Theorem. This was initially due to Fujiki, and then with some extra assumptions, and then Donaldson kind of rediscovered it, and also in a more general form. It's quite fundamental. He says that this action of this group of exact symplectomorphisms acting on this space of almost complex structure J, the omega naught if you like. This is a Hamiltonian action. With respect to this symplectic form omega, which we put on this large space J. Hamiltonian, remember, means that each infinitesimal generator of the action, each vector field which is a derivative of the action, has a Hamiltonian which can be chosen in a coherent way. So they can be you can put all these Hamiltonian choices together into a moment map. I think you will review it tomorrow, if I understand correctly, in the GIT lectures. And the moment map for this Hamiltonian action, so this coherent way of choosing Hamiltonians for all infinitesimal generators is given by the Hermitian scalar curvature. Which is not exactly the same as the Riemannian scalar curvature that we've been discussing so far, but becomes just the scalar curvature we discussed previously whenever the underlying J, the point, is an integrable, almost complex structure. So you should think that you have some, maybe write it down here. And actually, we will only discuss this integrable case in any way, so we don't actually need this more general result. You should think that there's a locus inside this big space J which parameterizes just integrable structures. So you have J int inside J, which is cut out by the equation, by the integrability condition that T01 is involutive. And this is a nonlinear condition which cuts out some infinite dimensional sub-variety inside J. It's singular, but it has some smooth locus, at least, on which this Hamiltonian construction restricts. And for J inside this integrable locus, the Hamiltonian is just, the moment map is just the usual scalar curvature we discussed. So it's S omega J, say minus a constant, and let me choose this constant to be the average of S. So this is up to a constant, of course, since the moment map is defined by differential condition. You can add constants, but you need to choose a constant appropriately, so that at least in principle the zero locus of the moment map is non-empty, and this is the only choice you can make for this constant in this case. And this is just the scalar curvature we had before, so it's a scalar curvature of metric, and the Riemannian metric defined by omega and J, by plugging in J in the second index. Okay. let me just remind you what needs to be proved. This is also, although I'm going to tell you the statement you need to prove, and that's also, so I'm going to review what a moment map is, although obviously in a very special case, but I think you will see the general theory better tomorrow. So, what do we need to prove? So, okay, this is a moment map condition. What is it? So, first of all, you should notice that the Lie algebra of this group of exact symplectomorphisms is just given by C infinity functions on M, which are normalized to a zero average with respect to omega naught, because we define this group G to be given by Hamiltonians, by functions. So infinitesimally they are given just by a function which you can normalize up to a constant, and you may choose that constant as you like. You can make it so that it's zero average. So Lie algebra is C infinity functions. So you can identify, there's a sort of killing form, so that you can identify the dual, or at least ignoring functional analytic aspects which we don't really need at all, the dual of this Lie algebra with the Lie algebra itself. So using the L2 inner product, which is the following. If I have two functions, I'm going, the L2 pairing is of course just the integral over M of the product. They are real functions with respect to the volume form which is defined by your symplectic. So in this, you use this to identify the dual of the Lie algebra with the Lie algebra itself, and so now the moment map takes values, remember, as you will recall, in general inside the dual of the Lie algebra, but we see it as taking values in the Lie algebra of the group itself by this construction. Okay, so moment map. Let me call it maybe mu. This is valued from J to dual of the Lie algebra, but actually, let me call this Lie G by identifying as usual, as we did here. Okay. And what is the condition satisfied by the moment map? It's spelling out what I was saying was before, that it gives you a choice of Hamiltonian for each infinitesimal generator in a coherent way. So, what does it mean in this case? I write it down here because I think it's important and more visible, this condition, and then we can try to check it again. Condition is this one. That if I take the derivative at time 0 of this function, which is given by variation of the almost complex structure, I pair it with anything using this L2 pairing. This is the same as the infinitesimal action. So the infinitesimal generator for the action of the group of exact symplectomorphisms, which we said is just given by this, again, J dot, where, say, JT is say some one parameter is a path, is any path with jt is not equal to j naught. See, we take any path starting at some reference integrable complex structure. J dot is its tangent vector to this path, so it's a first order variation of the almost complex structure. This is it's not hard to check that this is the infinitesimal generator for the action of G, this group of exact plectromorphisms, evaluated at the point J naught. Okay. This is, I think my reference point is called J. It's the same that appears here. So this is an infinitesimal generator for the action of G on this space. This is pretty intuitive, right? That you want to understand how what is the tangent vector along the flow of this action. It's just given by taking the Lie derivative of J. And this is the moment map condition, right? It's just saying that on this side I have the proposal for our moment map. This is the moment map side. It says that, okay, your choice of moment map should give you a choice of Hamiltonian for each for the infinitesimal generator of any for any infinitesimal generator of the group action. So for any phi, you should get a Hamiltonian for the action for this vector field by coupling with your moment map, proposed moment map. So this is what needs to be shown, and it's a good place to stop now. So maybe we can see something tomorrow.
Great. So questions for Jacopo?
Please.
So a few boards back, you had a statement about a theorem for, like, you fix a polarization, right, and then you build a moduli space for the complex structures that match that polarization.
Yeah.
So then have people tried to, like, I've seen this for other types of moduli spaces where you say, okay, I fix something and then I build the moduli space for that, and then I try to say, okay, now if I have all my polarizations, can I somehow glue the moduli space for each polarization together in like some nice way to build like a master moduli space?
Yeah, I see. Yeah, of course. So if you vary the polarization, I think much is known. So if you from this differential geometric perspective, the question is, okay, suppose you can solve your equation that the scalar curvature is constant in some Kähler class, and then you try to move the Kähler class, right, a little bit. And in general, the problem is abstracted. You cannot keep your equation if you different. But so the abstraction are coming from the group of Hamiltonian automorphisms of the given structure, which we will see tomorrow. But I mean, people are studying this, and it's interesting to see what happens when you vary the polarization. You should get some, of course, as usual in this business, you should get some walls and some kind of wall crossing behavior and so on. It's being studied actively.
Anything else?
Please.
So in this last line, you put that J is should be integrable.
Yeah, that's true. This is both the start. The whole path is inside the integrable locus.
So, but then I don't understand, because in the theorem you claim that the action is Hamiltonian just on the integrable?
No, the action is Hamiltonian, and the moment map is given by a different quantity in general, which is called Hermitian scalar curvature. It's the curvature of the Chern connection, which in general is not the same as the Levi-Civita connection. But on the integrable locus, they agree. And so all I'm saying is that in general here you would have this more complicated, different quantity, which is the curvature of the Chern connection. But since we are interested in genuine Riemannian metrics and in the curvature, we're interested in integrable complex structures more than anything. And other people are interested in non-integrable things, for sure. theorem is important in the non-integrable case too, I think. It's just as important. Please?
In that theorem,
Yeah.
is the constant the same for all the elements, or you just mean it's constant?
Yeah. It's so if this constant I didn't say, but it's if you integrate, it's the integral of the average of the scalar curvature is fixed because.
But it is fixed not just for nj omega at any point, but also for any nj omega is the same constant.
Yeah, it's the same constant because we had that fact that the Ricci curvature represents a fixed cohomology class.
Yeah.
So if you work with that a little bit, you realize that if you integrate this against the volume form, you get some fixed quantity independently of the.
And if you replace this by extremal instead of just CSEK, extremal.
Yeah, no. So if no, I think Rui is the right person.
That's no problem. That's a
No problem.
question. Maybe we'll thank Jacopo again.
Thank you.